Myself, I am Keshwan from CSC Section B. My topic is an amplified spontaneous emission model for quantum well-distributed feedback lasers. Abstract. An amplified spontaneous emission model for quantum well-distributed feedback lasers is presented, which takes into account local spontaneous emission, stimulated emission, and real refractive index change, which are calculated from the Fermi-Dirac occupancy functions in a self-consistent manner. The local normal mode transfer matrix method is used, which allows a coupling of the local DFB effect with the local spontaneous emission and gain. As an example, an analysis is given of a partly gain coupled DFB laser with periodically etched, which has a large discontinuity of spontaneous emission and gain in high and low correlation regions. It is shown that the side mode suppression improves with the increase of the number of etched due to carrier density dependent gain coupling. Introduction. Multi-quantum well MQW distributed feedback lasers have been developed intensively as suitable light sources for long haul and high bit rate optical communication systems. As a consequence, there are strong demands for detailed models of MQW lasers for design optimization. Recently, several groups have reported laser parameter extraction from the below threshold spectrum of DFB lasers. Theoretical models for the below threshold spectrum of DFB lasers have been developed by Soda and Imai and Makino and Glinsky with the use of the multiple reflection method. A more fundamental theory for amplified spontaneous emission ASC of Fabry-Perot lasers has been developed by Henry based on the Green's function method. This theory takes into account the longitudinal non-uniform distribution of laser parameters, and ASC theory for multi-selection DFB lasers has been developed by Makino with the use of transfer matrix method. For multi-section DFB lasers has been developed by Makino with the use of transfer matrix method based on Green's function approach. This model has been applied to the below threshold spectrum of partly gain coupled DFB lasers. Hansman has reported the analysis of DFB laser spectra above threshold, taking into account spatial hole burning with the use of the multiple reflection method. However, in these works, stimulated and spontaneous emission and stimulated and spontaneous recombination are manuscript received October 29, 1996. Revised February 5th, 1997. The author is with Norton Technology, Ottawa, Ontario, Canada. Publisher item identifier treated as phenomenological parameters are not calculated from the first principle using the Fermi-Dirac occupancy functions. Amplified spontaneous emission model. Consider a general DFB laser structure in which waves propagate primarily along the axis and the transfer electric field component as a polarization vector in the xy plane. Number 1. Amplified spontaneous emission power. Number 2. Approximate mode power. Number 3. Quantum well parameters. Application of partly gain coupled MQW DFB lasers. Partly gain coupled DFB lasers with periodically etched QW have exhibited high single mode yield, high power single mode operation, and wide temperature range single mode operation. This gain coupling approach has also been shown to be critically important for WDM laser arrays and laser sources integrated with external modulators. The schematic diagram of a typical gain coupled DFB laser with periodically etched QW is shown in figure 1. The detail of the laser structure is described in. The gain coupling is provided by the difference of a model gain between two corrugation regions consisting of larger and smaller number of QWs 5 and respectively in figure 1. In order to calculate the mode powers in this type of gain coupled DAB laser, an accurate treatment of local spontaneous and stimulated emissions is required as well as local DAB effects. Next, discussion. In the calculation of laser power in section 3, the SHB effect was ignored. This is a reasonable approximation for injection currents below to just above the threshold current. However, for currents much higher than the threshold current, the non-uniform distribution of photon density produces a non-uniform distribution of carrier density, resulting in a non-uniform distribution of a real refractive index. In this case, for a given injection current density, the local carrier density n of x, y, z needs to be calculated numerically with the use of the local photon density given by C2 as well as with use of non-radiative recombination current. This is not discussed in this paper. Once the local carrier density is found, the power spectral density can be calculated by a detailed discussion of the SHB effect is beyond the scope of the paper. Field generated by spontaneous emission. Following Henry's approach, we express the electric field generated by spontaneous emission by E of x, y, z, t. Where is the local spontaneous emission source? We assume that it has the following frequency and spatial correlations, where U of x, y is the transverse mode field, is the transversely averaged spontaneous emission source. The average ensemble power flow is given by the integration of the Poynting vector. Where is the magnetic field given by and denotes the complex conjugate? Where is the part of expressing the forward propagating wave? Approximate mode power. The mode power is given where the integration range is a free spectral range of the mode given. As the carrier density approaches the nominal threshold value, becomes very small due to stimulated emission for giving rise to the building up the mode. Noting that only is very sensitive to the mode power, where N and S are the deviations from the stationary carrier density and photon density satisfying W equals to 0 and Cn and Cs are defined. The integrand of the second equation is the Lorentzian distribution centered at with peak intensity proportional to. The third equation is derived based on that the Lorentzian distribution function can be approximated by the delta function when is very small. Partly gain coupled DFB lasers with periodically etched QWs have exhibited high single mode yield, high power single mode operation and wide temperature range single mode operation. This gain coupling approach has also been shown to be critically important for WDM laser arrays and laser sources integrated with internal modulators. The schematic diagram of a typical gain coupled DFB laser with periodically etched QWs is shown in figure 1. The detail of the laser structure is described. The gain coupling is provided by the difference of model gain between two corrugation regions consisting of larger and smaller number of QWs, when they are respectively in figure 1. In order to calculate the mode of powers in this type of gain coupled DFB laser, an accurate treatment of local spontaneous and stimulated emissions is required as well as local DFB effects. Discussion. In the calculation of lasing power in section 3, the SHB effect was ignored. This is a reasonable approximation for injection currents below to just above the threshold current. However, for currents much higher than the threshold current, the non-uniform distribution of photon density produces a non-uniform distribution of carrier density, resulting in a non-uniform distribution of real refractive index. In this case, for a given injection current density, the local carrier density n of x, y, z needs to be calculated numerically with the use of the local photon density given by C2. as well as with use of non-radiative recombination current. This is not discussed in this paper. Once the local carrier density is found, the power spectral density can be calculated by. A detailed discussion of the SHB effect is beyond the scope of this paper. Field generated by spontaneous emission. Following Henry's approach, we express the electric field generated by spontaneous emission by E of x, y, z, t. Where is the local spontaneous emission source? We assume that has the following frequency and spatial correlations. Where U of x, y is the transverse mode field, is that the transversely arranged average spontaneous emission source. The average ensemble power flow is given by the integration of the Poynting vector. Where is the magnetic field given by and denotes the complex conjugate. Where is the part of expressing the forward propagating wave. Approximate power, mode power. The mode power is given where the integration range is free spectral range of the mode given. As the carrier density approaches the nominal threshold value becomes very small due to stimulated emission, giving rise to the building up to the mode. Noting that only is very sensitive to the mode power, where N and S are the deviations from the stationary carrier density and photon density satisfying W equals to 0, and Cn and Cs are defined. The integrand of the second equation is in the Lorentzian distribution centered at with peak intensity proportional to. The third equation in is derived based on the Lorentzian distribution function can be approximated by the delta function when a is very small. Conclusion. A general ASC model has been presented for QWDFB lasers using the Green's function method combined with the transfer matrix method. The DFB effect and the QW stimulated and spontaneous emission effect have been combined in a consistent manner. The model can be applied to below to above threshold regimes without discontinuity, and also to multimode cases naturally without defining model photon density, since the power spectral density is used in the formulation. As an application example, a self-consistent calculation of ASC spectrum and the SMSR of partly gain coupled DFB lasers with periodically etched quantum bells has been reported for the first time. It has been shown that the main mode power increases more rapidly as a function of carrier density, and that the side mode is more increasingly suppressed. Thank you.